Here, of course, you see the view of the oceans. We live on planet ocean, not planet Earth. 70% of the oceans are water, and of course the greatest body of water is the Pacific, and of course the Southern Ocean that swirls around. And I will come back to the unique characteristics of the Eastern Pacific in the course of the talk. But let me try to motivate our symposium, the discussions yesterday and the discussions that will follow today. Why observe the oceans? And there are two basic reasons: more human activities and also possibilities for discovery. Let me begin by giving examples of more human activities, more uses and more users. These are derricks for drilling for oil in Singapore. These structures, which we now find on the Patagonian shelf and in the Gulf of Mexico and in Indonesian waters and in the North Sea, a structure, a civil engineering structure for offshore oil and gas exploitation now costs about $5 billion US. These are among the most expensive manufactured objects in the world. Singapore is very smart to be in the business of making them. Of course, fishing, offshore wind is starting to grow around the UK and other places. There are proposals to extract energy from waves in the oceans. Shipping, maritime transport. This chart begins in 1968. It goes to 2008, and you see the growth of different kinds of shipping, crude oil, iron ore, other cargoes. After the first oil crisis in the 1970s, there was a slump, but you see since then there's been a steady growth of shipping. So in billions of ton miles, we have gone from about 8,000 ton miles of shipping, 8 billion ton miles of shipping in 1968 to about 4 times that in 2008. And ships larger than 100 gross tons, in 1960 there were about 36,000 large ships in the world. Today there are about 100,000 large ships. These ships travel many places in the oceans. The Atlantic is covered with shipping. The Central Pacific, the Eastern Pacific is unusual in it's relatively pristine from that point of view, and of course also the Southern Ocean, still less shipping. But the growth of humanity the past 10,000 years, it's a story of ever more red lines, and usually noisier ships with bigger displacement, greater bow waves. Here is a slide for our hosts from Telefonica. The oceans are important not only for marine transport, but in fact the oceans are the key to telecommunications. We often think of satellites. We speak into a cell phone and we think that the communications go through the air, but most communications go through cables on land or under the sea. This is a slide developed by Dutch colleagues showing the cables on the seafloor for telecommunications. Because it's difficult to place cables on land, increasingly the telecommunications companies are scalloping the cables along the seafloor on the edges of the continents, around Africa, around South America, around India. And so with the growth of telecommunications, we can expect the oceans to become, again, more important, more structures on the seafloor. I mentioned already offshore oil and gas. This is by far the largest industry in the oceans in terms of its value in cash. We think of fishing, we think of shipping, but offshore oil and gas is already the largest industry. In the US alone, the infrastructure for offshore oil and gas, primarily in the Gulf of Mexico, has a value of about $20 trillion. We see structures on the surface, but every structure on the surface connects to a spider web of structures on the seafloor, complicated, extensive structures. Building these structures involves seismic testing, drilling, engineering and construction to make the subsea facilities, the surface platforms, and of course many remotely operated vehicles. Most of the remotely operated vehicles in 2010 do not belong to navies, they do not belong to research institutions, they belong to the companies in the oil and gas industry that are building and inspecting and operating the offshore structures. The offshore structures are exceedingly dense and complex. Here is the city of New Orleans, here is Houston. These are the network of pipelines on the seafloor in the northern Gulf of Mexico. The Deepwater Horizon spill, which I will speak about a little bit later, occurred about over here. So the increasingly the seafloor in the North Sea or in the Gulf of Mexico or in Indonesian waters, in the South China Sea, in Brazilian waters, south of the Petrobras structures, south of Rio, they now look like the railroads of England or of Germany 150 years ago. So there are very extensive, complex structures that, of course, are very important for obtaining the energy in ways that are resilient, but also with consequences, of course, for life, for biology, and other aspects. Let me mention one other area of particular interest to me and some other people in the room, including Nicholas Macrease and Olaf Runeguda, and that's noise. In green, you see the natural and biological noise in the ocean, from the rain falling on the surface, from ice cracking, from the noise that the animals themselves make, from seafloor earthquakes. And here you see in blue the additions of noise from shipping. Essentially there was no human noise added to the oceans in the year 1850. In 2010, human additions of noise to the ocean will probably about equal the natural sources of noise in the ocean for the first time. We are increasing by about 3 decibels per decade the human noise added to the ocean, which is roughly a doubling of the noise as energy each decade. We speak about global change, we think about climate, we think about acidification in the oceans, but in fact the addition of noise to the oceans is also one of the great global changes, and if we keep adding, well, I think it's just, it will be impossible, I think, for environmental and other reasons to continue to double the amount of noise we add to the oceans each year. Our most, our deepest images of the ocean are usually about ocean life and the experiences we had as children, as young people, often playing at the beach or fishing. Recreational fishing is a kind of sampling, not completely scientific, but it's a kind of sampling of what lives in the oceans. Here you see a photograph in 1958 in the United States, in Florida, in South Florida, of a family, 2 adults and a child, on a vessel called the Greyhound. They've gone fishing for the day. They've caught these enormous groupers. Here's a photograph in 2007 of the same recreational fishing enterprise, the Greyhound, and you see the size and diversity of the animals has changed. Of course, we want to go from anecdotes to science, and in the Census of Marine Life, our colleagues have looked at many, many studies, and if you go back to the year 1000, up to the year 2000, you find that there were gradual declines in coastal populations, in abundance and diversity, for example, of cod, turtles, whales, seabirds, oysters, and then beginning about the year 1800, a series of collapses of populations. and in some cases extinctions, or local extinctions at least, so that and yesterday from Daniel Quiros and others here, we heard about Chilean experiences. So there's a pattern, I would say a pattern of serial decimation of populations. Okay, so I've spoken about the reasons to intensify our observation of the oceans because of the increases in human activity. But it's equally important, as in observing the stars, part of science is exploration and discovery. And the exploration and discovery of the census of marine life has been thrilling beyond imagination. And I'll just give a few examples of some of the animals we've discovered. We've also discovered behaviors, populations, and speakers later today will talk about those aspects. I begin with the iconic animal, the Yeti crab, discovered by the deep sea team, of which Chris German here is a member. And this was discovered, of course, in the Mar Presencial of Chile, south of Easter Island, about 100 degrees west, 37 degrees south. This fantastic so-called Yeti crab, which now also appears in paintings and on skateboards and as a stuffed animal already in aquariums, although discovered only about 5 years ago. In the deep North Atlantic, the team of which Olof Rune Goda from Norway is a member, made spectacular discoveries. This deep sea octopod. The North Atlantic is the most traveled, the most traversed sea. It would be easy to believe that there is little more to be discovered in the North Atlantic, and yet if we look down 1,000 meters, 2,000 meters in the North Atlantic, we see spectacular animals that we have never seen before. In the South Atlantic, the group led by Pedro Martinez that studies life on the abyssal plains discovered hundreds of new copepods of incredible beauty, exotic, like science fiction. Pedro will speak more about these animals in his talk later today. But for me, seeing these animals is like going to the finest jeweler in Paris. It's like going to Cartier or Baccarat, the extraordinary beauty of the animals. And strangeness. This is a sea cucumber discovered by the zooplankton team of the census in waters between Indonesia and the Philippines. Another example from the Indonesian waters, a new polychaete squidworm. And in shallow waters also, the waters we make discoveries not only in places that are hard to reach, but also, for example, this beautiful octopus just discovered just 2 years ago off northeastern Australia. And even in the United States, in shallow water, in water only about 2 meters deep, a new kind of kelp was discovered, the golden V kelp. And this can grow to 2 meters, even 3 meters in length. Now, I should say these animals are not only interesting, some of them have remarkable physiology. For example, some of the animals live 500 years, 600 years. So if we are interested in immortality and regenerative medicine, some of the animals are interesting. Some of the animals live in anaerobic conditions. The first anaerobic animal was discovered. So the animals are interesting not only because they're beautiful, although beauty, I think, is a great motivator and extremely important in the understanding or trying to protect nature better. But the animals also have characteristics which are important for science. Well, as a whole, the census concluded that there are about 250,000 known species with Linnaean names, with Latin names like Homo sapiens for humanity, and we estimate that there are at least 750,000 more to discover. And this, of course, is part of the challenge for observing marine life. In this sense, it's different from observing hurricanes. How does one observe 250,000 known species? How does one observe 750,000 species that we have not yet discovered and described? So we need programs that both can monitor what we know, but also can explore and be open, alert to identify the unknown. And of course, this is a world of complexity, of three-dimensional and four-dimensional complexity, because the animals move, as George Schillinger and other speakers later today will say. So globally, I think we need a global ocean observing system. GOOSE, it is called in the world of acronyms of international cooperation in science. And GOOSE must include a strong biological component, a marine life observation network. Of course, we also want a global ocean observing system so we can improve predictions of El Nino, so that we can better understand how an oil spill may disperse. But let me just give today just motivate our concern with marine life. And let me give some of the examples of some of the benefits that we can have by observing and aggregating our observations of marine life. This is a map of the Caribbean with Cuba and Haiti and Dominican Republic, Puerto Rico, Venezuela, Colombia, Belize. This is work by our Caribbean team led by Patricia Miloslavich from Universidad Simón Bolívar. And you see Patricia and her colleagues aggregated records from 5,600 species. And when one does that, one finds hotspots, for example, on the Colombian coast or the off Belize, off Cuba, some around Puerto Rico. And these are areas that we believe merit special protection, special environmental protection. They are, in the jargon of the United Nations, ecologically and biologically sensitive areas, or EBSAs. And the Convention on Biodiversity, the International Treaty about Biodiversity, the CBD, calls on nations to identify EBSAs in their own exclusive economic zones and also in the high seas shared by all nations. So we need an observing system that will identify and monitor these environmentally and biologically sensitive areas. The census, for the first time, put together global maps of hotspots, of areas of special interest, special intensity, density of biodiversity. Here you see a map prepared by Derek Tittenzor and colleagues, a network led from Canada, from Nova Scotia, and you can see in red the areas which have the highest known biodiversity for all taxa, for coastal taxa, near shore, and then for the open ocean taxa, including this area off Chile in the Humboldt Current. So it was possible to do this, again, only by thousands of people working together, sharing millions of observations to create these global pictures. At the same time, I don't want to exaggerate the quality of what we know. Our knowledge is advancing. The known is better than it was 10 to 20 years ago, but as Francisco Godoy reported yesterday, there are still, in fact, many gaps in the picture. So here is a more honest map, in a sense, than the one I showed you yesterday, where, again, red indicates high biodiversity. If you took a sample of 50 animals out of the ocean, you would have high biodiversity, and blue would represent low. And white really means that there aren't enough records, in fact, to make a judgment. And so, as Francisco showed us yesterday, the Eastern Pacific, in fact, is still from the point of view of marine life, and also from other point of view of other concerns. More broadly, one can say the Southern Ocean, about which Michael Stoddard will speak later. The Eastern Pacific and the Southern Ocean are still the least explored. So we need our statements about these areas are tentative. We have lots and lots of measurements around in this area or off the northeastern United States, but there are still large parts of the world for which observation is discovery. Let me give another example of benefits of observations. I mentioned earlier the oil spill in the Gulf. Happily, in the year 2009, the team preparing the survey of the Gulf of Mexico completed its work. They found more than 15,000 species in total in the Gulf of Mexico. This was work that involved, produced a beautiful, big, thick book, which is available online also. And they produced maps. Here you see Cuba, Yucatan, Cancun, where the climate negotiators are meeting now, Mexico, Texas, Louisiana, Florida. The oil spill on the 20th of April occurred about here, and our colleagues in the Gulf of Mexico project had prepared a list of exactly 8,332 species observed to live in this slice of the pie of the Gulf of Mexico. So as the U.S. Environmental Protection Agency now works on impact statements about the effect of the oil spill before and after, and Chris German here in the room will be visiting some of the deep areas with the Allen submarine just in the next few days. At least we have a list of what lived there before, and certainly in areas like the Indonesian waters, the Patagonian Shelf, the waters on both coasts of India, which are starting to be exploited offshore, preparing these kinds of records, and certainly there's plenty of methane on the continental margins off Chile. If there's going to be exploitation of natural gas, it's very important to have these baseline surveys so we can assess changes. Let me give one more example of assessing changes. There's tremendous concern about warming of the oceans, changing currents. Our colleagues in China, in Qingdao in China, which is the sort of Concepcion or Woods Hole of China, made very careful measures beginning in 1990 up to 2010 of populations of jellyfish in that area, and you see that since about the year 2001, there has been a series of very high peaks of populations of certain jellies. So again, if we want to observe changes that may come with warming, changing currents, acidification, more noise in the oceans, more light at night over the oceans, other changing chemistry, then we need to look at more than just some of the famous fish. We need to look we need to really to be observing many phyla, many species. Finally, along these same lines, relationship with temperature. Again, we talked today while thousands of negotiators are negotiating about the Framework Convention on Climate in Cancun in Mexico. We all know that marine life is sensitive to temperature. We are also marine animals, at least in the summertime. We go swimming when the water is warm. When the water is very cold, we stay away. Well, of course, as birds migrate, many animals migrate and move and are obviously sensitive to temperature. Here you see relationship of biodiversity to sea surface temperature for all taxa, for coastal taxa, and for open ocean taxa. And clearly, most marine life cares what the temperature of the water is, and so it's clear that climate change would bring a great redistribution of marine life. At this time, it's very hard to say in detail what it might be. So, I've tried to make the case that we need a marine life observing network as part of the global ocean observing system. Such a network, such a system might include nearshore long-term sites. Our Japanese colleagues have pioneered ideas in this area. Chile itself has participated in these programs. The idea is to have long-term ecological monitoring sites in relatively pristine areas of the shore where the measurements would be made very, very carefully in the way that the Japanese themselves exemplify. And globally, we should have maybe 200, 300, 400 such stations, which could give us very clear ideas of changes in the nearshore environment. Reefs, obviously reefs are of enormous interest. They are a celebration, the most intense exemplification of marine biodiversity. There are new technologies called autonomous reef monitoring structures. They are a bit like the doll houses of young children, empty doll houses. Animals move into them. It's a very inexpensive and standard way of measuring biodiversity of reefs. And already there are some 600 of these autonomous reef monitoring structures around the world. This population should grow and be examined regularly, shared databases. The continental margins of great interest, obviously, to Chile. The margin is very close to shore, very geologically active. The Census of Marine Life, under the leadership of Miriam Sibue, and also including Chilean scientists, again developed standard protocols for measuring diversity as well as distribution and abundance on the continental margins. We'll be hearing from Pedro Martinez about the vast abyssal plains, the largest habitat on Earth. Yesterday we heard about seamounts. Of course, Chile has fascinating seamounts which are exploited for orange roughy and other fisheries. The ocean ridges, the East Pacific rise, vents, midwaters. We need to develop some kinds of life gauges appropriate for each of these environments that will yield a continuing record of changes in ocean life. The census integrated its picture of the ocean, rich with technology, including divers and filmmakers like François Saronneau filming animals on the surface, people in submarines, submersibles with cameras, fish with cell phones and GPS, acoustic listening devices. This picture tries to give a kind of summary of what just for marine life, what science can bring. Obviously, one also wants to measure temperature and salinity and so forth. But when Victor Gallardo speaks about an observing system for the Eastern Pacific, something that might be coordinated, anchored, led by Chile, I think from the point of view of the Census of Marine Life, we see an ocean alive with human observers and technologies like this, including down to the ice. Let me conclude again by reminding you that for all the progress ocean science has made, we do need to think both about observing those things that we know and about creating a system that will see things for the first time, because again, much of the ocean is unexplored. So when we are not only repeating measurements, when we make measurements, many measurements we make will be measurements of discovery. We will find things that we've never measured before. This is a map showing most of the records compiled in the main census database. The blue records, the blue dots, represent information that the census collated, we can say from the time of Aristotle up to the year 2000, data sets from many sources, from fisheries agencies, from explorers like Darwin or Humboldt. The yellow records represent areas where the census made lots of observations in cooperation with other groups already making routine observations. while the red, and you see this tremendous activity here and over here, represent areas that we tried to look where there were essentially no records before. I've shown you horizontal maps of the ocean. My next to last slide shows you a vertical slice of the ocean. So here is the near shore, here's the coastline, and in red or yellow you see areas where there are many measures, many records in the census database. And so you see near the shore and near the surface and on the sea floor we have, this is mostly where ocean science has worked. As we go deeper, as we go to 4,000 meters or 5,000 meters or 6,000 meters, as we go farther out into the open ocean, these blue spaces are gaps where essentially we have no records. So the vast midwaters of the Eastern Pacific, for example, are largely unexplored. This is my last slide. Earlier yesterday and earlier today, we have seen this view of the unexplored ocean going from Chile, Antarctica, New Zealand, Australia. This is with 5-degree squares. If we go to 1-degree squares, we see an even more, I would say, exciting picture for science, but challenging picture for monitoring. That the Eastern Pacific, parts of the Southern Ocean near to Antarctica, from the point of view of marine life, they are still terra incognita, or virgin territory, or unexplored ocean. So on the one hand, in conclusion, I would say the census is immensely proud to have collected millions of records from all of our colleagues in the past, to have helped conduct more than 500 expeditions, to add many new dots, many new reference points. But we also, in 2010, we are still very humble and modest about the immensity that is the oceans, the huge challenge to take the technologies that the census has pioneered, to continue the exploration of the unknown ocean, and also to put in place measuring systems that will tell us about the changes in marine life and other aspects of the oceans that are important for humanity during the decade to come. Thank you very much.